So today we're going to go over what we call a linear classification of homogeneous linear systems. So the main goal is to establish the stability of equilibria, or the equilibrium point, because you will see most of the time the only equilibrium point is the origin for homogeneous systems. There are special cases when you have actually infinitely many equilibria, as you will see today. But the main goal is to establish the stability, whether the solutions converge to the equilibrium point or not. And also some geometric descriptions of solution trajectories. So how the solutions, generally speaking, look like around the equilibrium point or overall in the phase plane. And how we can infer that shape or the geometric description from just looking at the solution of the homogeneous system. So looking at the eigenvectors, the eigenvalues, whether they're real or complex, all of these will have some impact on how the trajectory looks like. So that's important for two reasons. Once you see the picture of a solution, you can infer something about the original system. For example, whether you have some periodic motion or not, that will tell you something about the eigenvalues, for example, right? I mean, it means that you have complex eigenvalues because that's when you have the periodic functions as part of the solutions, sine and cosine. And another important reason, probably the more important one, is that, as you will see in the last topic of this class, we could use linear systems, homogeneous linear systems, to approximate the local behavior of nonlinear systems. So you can look at the equilibrium point of a nonlinear system and you can approximate in some cases what happens around that point with the aid of a linear system that approximates the nonlinear one. So that will be the last topic of the class. So this is a complete classification. We're going to provide examples for each case and the solutions of each case, right? So I'm going to provide a system and the solution of that system. I'm not going to go over the details on how to find the solutions. You can actually do that on your own, just to practice with what we talked about in the previous lecture. The focus today is to go through all of these examples, and it's very important right after this presentation to take a look at the presentation on the computer, because I'm going to run each example on the computer with a plotter, and you should do the same, okay? So make sure you enter all these cases in the computer to get familiar with the shape of the solutions in each case. You will have a formula sheet with this classification, but not with the pictures. So you don't have to memorize the terminology for each case, but you need to know how the solution looks like in each case, to have an idea on how the solution looks like, depending on whether you have real eigenvalues or complex eigenvalues and so on and so forth. Most of the different cases in terms of the geometry of solutions happen in the real case, real eigenvalues case. The complex case, there are only three cases essentially to discuss. So we're going to start with the real eigenvalues case. And so you will see lots of separate subcases to begin with. But let's start with an example right away. So I'm going to actually number these cases. I forgot how many actually are in the real case, but there are plenty. And again, I want to emphasize, you will see lots of pictures in this presentation, but it's important to run the case with the plotter, because the picture will be definitely better. I mean, my drawing skills are limited, to say the least, so I'll just emphasize the main idea on how the picture looks like, but it's really important to run each example with the plotter, so to really see the shape I'm talking about. So in the first case, let's take one situation when you have distinct eigenvalues, both positive. Distinct. So here's an example. So we're going to provide an example for each. The matrix of this system is 2, 1, 2, 3, and the solution. And again, you can take the time to find it yourself and confirm. But the solution is C1 1 minus 1 e to the t plus C2 1 2 e to the 4t. So the eigenvalues, by the way, in this case are 1 and 4. So take a look at the exponents of the exponentials, and of course 1 and minus 1, 1 and 2 are the corresponding eigenvectors. So one thing I want to point out before I show you how the picture looks like in this case, notice that if I start with an initial point on one of the eigenvectors, and remember what we talked about last time, when I say the eigenvector, I don't talk about just one vector. There's a family of vectors. Any multiple of 1 minus 1 represents the same eigenspace. So basically when we sketch the eigenvectors in the phase plane, you really sketch the whole family of the eigenvectors corresponding to an eigenvalue. So in other words, it's a line in the vast majority of cases, right? So any multiple of 1 minus 1 will be an eigenvector. So any point on that line that connects the origin with 1 minus 1 will be an eigenvector. If you start with an initial point right on this eigenvector, so let's say x naught is 3 minus 3, which is a point on the eigenspace. 3 minus 3 is an eigenvector, just like 1 minus 1 corresponding to lambda equals 1. If you actually find C1 and C2, it's not hard to guess beforehand that C2 will be 0. I mean, we could actually verify this right away, that the solution of the initial value problem, if you start with this point, is going to be 3 for C1, 1 minus 1 e to the t, and C2 will be 0. You can convince yourself, you can set up the system, but it's not hard to guess that you're going to end up with this solution, right? I mean, if I plug in 0 for t, e to the 0 is 1, 3 minus 3, that's going to be my initial value. So, in other words, in the real case, and that's an important remark, which we should write it down, in the real case, the vector, the eigenvector, is invariant, which means that if we start on the eigenvector, and by that I mean the whole family of eigenvectors for that particular eigenvalue, we remain on it, roughly speaking. Okay. So if the solution, by we I mean the solution, right? So if the solution starts on the eigenvector, it stays on the eigenvector. Because notice that if you look at the solution by components, so let's actually write this by components, right? That's 3 to the t minus 3 to the t. No matter what the time value is, the relationship between y and x is y is equal to minus x. Doesn't matter what the time value is, right? It is always true that the first component is equal to minus the first component. So, in other words, the solution moves on a straight line. Another way of putting it is that eigenvectors indicate straight line solutions. So if you have a real eigenvector, basically that indicates a solution that is actually a straight line. What else can we say about the motion with respect to the equilibrium point, which is 0, 0, by the way, right? So I mean, the only equilibrium point for this system is 0, 0. Well, because the eigenvalue is positive, it's clear that you move away from 0, 0. So as t increases, when t is, right, I mean, when t goes from 0 to infinity, right, I mean, the solution goes away from, I mean, in forward time, the solution moves away from the equilibrium point because lambda is positive. Of course, if lambda will be negative, it'll approach 0. Because, I mean, e to the minus infinity is 0, right? So, I mean, if you would have a negative value here, this path will go to 0. As it is, then it moves away from 0 because e to the t goes to plus infinity. Now, of course, the sign of C1, means that you move in both directions, either along the line, above the line, and below the line. But the key thing is that you move away from 0 on that line if t is positive. If the eigenvalue, the coefficient of t is positive. So at this point, we can actually sketch the two eigenvectors for lambda 1 and lambda 4 and indicate on the eigenvectors how the solution moves. So for this case, we're going to have one eigenvector 1 minus 1. So that's 1 and minus 1. And I'm going to indicate with arrows away from 0 the fact that lambda is positive. So this is corresponding to lambda 1, right? The eigenvector corresponding to lambda equals 1. So if you start on it, you move away from 0 on a straight line. And the other eigenvector is 1 and 2. So x equals 1 and y equals 2 over here. And that corresponds to lambda equals 4 over here. Lambda equals 4. Okay, so that's what happens if you start on the eigenvectors. What about if you start at any other point on the phase plane? Well, on any other point, obviously both of these solutions will have an effect on the motion on that trajectory. So you still move away from 0, but notice that the effect of the larger eigenvalue is more pronounced. So this part here pulls the solution away from 0 faster. So the easiest thing you can think about is like the game of tug of war, so to speak. Imagine that each eigenvector pulls the solution along its line away from 0 if it's positive, if lambda is positive, and towards 0 if lambda will be negative, as you will see in the later cases. But the size of lambdas matters because this guy wins, right? I mean, this guy pulls the solution away from 0 much faster. So you will see in the plotter that if you click on a point over here, the solution will kind of look like this. They will look almost parallel to the eigenvector corresponding to the larger eigenvalue. So sometimes we call this the fast direction because, or the faster eigenvector or eigenvalue, because it pulls the solution away from 0 much faster. If the difference between the lambdas is even more pronounced, you will see these lines almost parallel to the fast eigenvector, because again, e to the 4t increases much faster than e to the t. So that's roughly speaking the shape of the solutions around the equilibrium point. Obviously, this is a case of an unstable point, right? So 0, 0 will be unstable. That's just to indicate that the solution moves away from it. But to have a more detailed description, you'll also call this point a repelling node or unstable node. Node is the generic name of equilibrium point when you have real eigenvalues. So repelling node, again, the clue is in the title, means the solution moves away from 0 from all directions. Again, a little bit faster along the larger eigenvalue. So with these details out of the way, let's move on a little bit faster on other examples because you will have variations of this. So let's do the complete opposite of what we have here. Let's say I have negative eigenvalues and distinct. Just to tell you a little trick of the trade, if you want to have the same eigenvalues but with opposite signs than the previous example, you just have to interchange the signs on the main diagonal. So that's how you can create some quick examples for yourself. So x prime would be, let's see, make sure I put the right example. So minus 2, 1, 2, minus 3. Minus 2, 1, 2, minus 3. I ran these examples before, but I want to make sure I don't mismatch them with the wrong case. So, by the way, the eigenvalues will be minus 1 and minus 4. You can check. The eigenvectors, though, will change, will not be the same. So, I mean, eigenvalues are predictable. If you change the signs on the main diagonal, they will be the opposite of the previous ones, but the eigenvector won't be the same. So, in this case, the solution is C1, 1, 1, e to the minus t plus C2, 1 minus 2, e to the minus 4t. So you have the same idea that e to the minus 4t is faster than e to the minus t, but now in the opposite way, it pulls the solution towards 0 along these eigenvectors. So if you sketch the eigenvectors now, corresponding to minus 1, you have 1, 1. So that's the eigenvector corresponding to lambda minus 1. And the other one is 1 minus 2 over here, corresponding to lambda equals minus 4. So now if you start on the eigenvector, you move towards 0, right? So the arrows indicate motion inward towards 0. And again, if you start on any other point, you should see the solution almost parallel to the fast direction, kind of like that, towards 0. Again, we're going to run these examples with the plotter because this is really rough with the empty hand, so to speak. So just the opposite picture of this, along the fast direction, solution approaches 0 faster. So this will be, of course, a case of a stable point, stable equilibrium point, and this will be an attracting node. So that's an attracting node, and of course we're going to continue with the other cases in the second part. We're going to deal now with positive, negative eigenvalue. Then what happens if you have a single eigenvalue and a single eigenvector? Single eigenvalue, two different eigenvectors, you know, the so-called star node we discussed before. And the 0 eigenvalue is also a special case that is worth talking about because the shape of the solution looks quite different in that case. And then we're going to finish with the complex case. So stay tuned for the next part.